then the information isn't damaged. It's only an unseen event in which a particle leaks out. Particle damages quantum information. So, in fact, if we scale the system up, then we keep the time scale by which we take snapshots of the system fixed, then the probability of an unseen error due to a particle propagating across the sample does get exponentially small, and we can preserve the information well. I'm running out of time, so I think I'm going to really not discuss this slide. This is something Gottesman will tell you about. If the noise has nice properties, if the noise is sufficiently weak and not too strongly correlated, then we should be able to perform a quantum computation accurately. So with some fixed probability of failure, we can, with a reasonable overhead, once the noise is weak enough, do the simulation. And one of the ways of doing that is to use these topological codes, which I've just been describing, not the only way, but it's a particularly nice way. And you can think of qubits arranged in a plane, which they're not necessarily interacting particles described by some local Hamiltonian, but we can in fact simulate the physics of a topologically ordered system using any hardware that we think is highly reliable, like superconducting qubits or ion traps, and protect the quantum information stored in the system for a long time, which enables us to do reliable, scalable quantum computing. It will only work if the probability of error every time we do a gate is sufficiently small, and if we use a naive model of the noise in which each gate is either ideal or introduces some depolarizing error on qubits, that critical probability of error per gate is not terribly small. It's a little bit less than 1%. And so there are many practical considerations to scaling this type of thing up. And then very daunting engineering considerations. And of course, at this point, we only can experimentally control well small numbers of qubits. If we want to do scalable quantum computing, we'll have to be able to do it for very large numbers of qubits, thousands or millions. But at least in principle, we've understood that if the noise is weak enough and not too strongly correlated, we know how to do scalable quantum computing. And that'll be a great challenge in the next few decades for people who are trying to scale quantum systems up. And I'll skip this part. And then I'm going to skip this part too. But I did have a couple of slides in which I wanted to say there's a lot more to this field than trying to build a quantum computer. As a physicist, I'm very interested in the implications of quantum information for understanding other problems in physics which don't have anything directly to do with building powerful computing machines. And I was going to tell you something about how we can use entanglement to characterize quantum phases of matter, and something about how we can use ideas about quantum error correction and quantum channel capacities to get some insight into how information gets processed by black holes in systems where quantum gravity effects are strong. That's actually how I was into this subject. I got interested in quantum information processing by thinking about how black holes process information. And we can also maybe gain insights into fundamental physics by thinking about simulating fundamental processes, as I mentioned earlier, like quantum field theory and quantum gravity. So let me just end with a few questions for you to think about, because I don't know the answers. I would like to know. You could ask, if we already know that we've reached the era of quantum supremacy, can we say that there are things that nature is doing now which seem to go beyond what can be done with classical digital computers? It seems like nature solves hard problems in some physical systems, like strongly correlated materials and complex molecules. Was that an illusion? Is it possible to actually simulate these systems classically? We just haven't figured out how to do it yet. Now, in the near term, we're not going to have systems with 10 million qubits like the factoring engine I described at the beginning. Maybe we'll have systems in the not-too-distant future with a border of 100 qubits. Can we convincingly demonstrate quantum supremacy that these systems can do things that classical systems can do in the reasonable near future, which is the border of 100 physical qubits? Not enough for us to do full-blown quantum error correction, not necessarily enough to operate a universal quantum computer, but nevertheless, the physical system may be able to perform tasks like simulation or things like quantum physics that goes beyond what we can do classically. I'd like to know if we can build a quantum disk drive, a system which is protected against logical errors by a macroscopically large energy barrier. I mentioned the contrast between a ferromagnetic classical memory and a topologically ordered medium quantum memory. One really does have a storage time, which grows exponentially with the size of the system, because the domain wall has such a large energy cost. The other doesn't have that feature. The error rate is really determined by some energy gap, the cost of creating a particle which can then propagate across the system. We know a kind of theoretically robust quantum disk drive can be designed to be at 4 spatial dimensions, but we don't. And the answer is unclear in the case of 3 or 2 spatial dimensions. An important question for the future of electronic commerce is, can we find efficient schemes for doing classical public key cryptography where we can feel confident that quantum computers cannot attack those schemes successfully? A question we don't know the answer to is, how can we test quantum mechanics as part of motivation for scaling these systems up to explore quantum mechanics in a new regime? But if we're testing it, that means there's some alternative. And we'd like to know, can we perform quantum mechanics and get some testable theory that makes sense and is a plausible theory to test in an experiment? And finally, a question that you should all ask is, how do we envision quantum information science changing the world? Maybe the question is cringeworthy because it seems so grandiose. But I think part of what makes the subject so fascinating is because we're talking about capabilities of quantum systems that we can simulate. There's really a world of possibilities that we may not have imagined. And another question that you should probably ask, also grandiose, is how can you change the world? It's an important question to think about, and I hope you will. Okay, thanks. Performing routine tasks. But what scientists and engineers do today can have a huge impact on society 100 years from now or more. But maybe the hardest thing to decide if you're a scientist is deciding what kind of science you want to do, because there's so many exciting things to work on. You can try to understand the molecular basis of life. You can try to conceive information processors that are cheaper and smaller and faster that we can put in our shirts and our socks and affect everything we do. information in the microwave background. So they're always deciding things, but of all those things, you decided you wanted to study quantum information. Why? Does anyone give an answer? Why are you studying quantum information? Somebody must have thought about this question. Well, let's try to decide what the question means. What is quantum information? What is quantum information science? A lot of different answers to that question can be given too. Now, sometimes it's helpful to try to distill the subject to the fundamental question that it tries to answer. I used to do particle physics, and it's probably uncontroversial that the question that particle physics addresses is what's the underlying theory that explains all the observed elementary particles and their interactions, including gravity. And then from that are descended many more refined questions. Is there supersymmetry? How is it broken? Why is there CP violation? Why do neutrinos have mass? And so on. So we can try to distill quantum information to one question, and you might propose a lot of different ways of formulating that. But here's one way. The question we're asking is, can we control complex quantum systems? And if we can, what are the scientific and technological implications? In quantum information, we are exploring a frontier of science. It's not the frontier of very short distances, like in particle physics, or very long distances, like in cosmology. It is the frontier of highly complex quantum states, what we could call the entanglement frontier. Now, maybe this question doesn't capture everything that's interesting about quantum information science. There are a lot of things that we shout in a way. But I think it does get to the heart of what makes the subject so compelling. And it's the reason that I study it. So we, the quantumists, are rebels. We're rebelling against what stood as conventional wisdom for a century, and what we learned in school. This dualism between the macroscopic and microscopic. Big things like me are classical. Little things like atoms are quantum. What we're trying to do is push further and further into the macroscopic world and have quantum effects that we can control. Now, why do we want to do that? Why do we want to do that? Anybody have an answer to why we want to do that? Well, a succinct way of saying why we want to do it is because classical systems cannot simulate quantum systems efficiently. And that's not a statement that we know how to prove, either experimentally or mathematically, but we have reason to think is true. And what it means is that as we push quantum effects to larger and larger systems, those quantum systems can behave in ways that are hard to anticipate. They have the capacity to surprise us and behave in delightful ways. But there's this other big question that moves over the subject. Because if we're going to succeed in pushing quantum effects up to the macroscopic scale, we have to overcome this very formidable enemy, decoherence. Decoherence is really responsible for the distinction between the macroscopic and the microscopic. These systems are classical because no matter how we might try to prevent it, they inevitably interact with the environment, and that causes the system to behave classically. So if we're going to reach our goal, we have to beat this enemy. And the question that moves over the subject is that merely really hard, so that if we spend a lot of effort over decades, we'll finally succeed. Or it might in fact be ridiculously hard, so hard that we won't succeed for centuries, or possibly ever. So our goal, certainly one of our goals, is to push quantum information into this new phase, to enter the era which we can call quantum supremacy, where we can prepare and control quantum systems that behave in ways that we can't necessarily successfully predict using digital computers. Those are the systems that have potential power to lead us to new discoveries. And so that means that we need to gain a deeper understanding, if we're respectful, of two basic questions. What are the quantum tasks that are really feasible? And that's partly a question about science, that's partly a question about engineering as well. What can we really do with reasonable resources in a system that we can build? And I think the boundary between what's engineering and what's science is not clearly defined. And we'd like to know what are these quantum tasks that are hard to simulate classically. Because that's what we should reach for, to do things with quantum systems that we couldn't otherwise do. And it might turn out that, although we think, based on our current understanding, that quantum systems have capabilities and perform tasks that go beyond what we can do in the classical world, it might turn out to be wrong for any number of reasons. Maybe because of principles of physics that we just haven't discovered yet. So the subject emerges from a convergence of several things, which occurred roughly aligned in chronology. One, which already goes back a couple of decades, is growing concern over the future of silicon-based digital information technology. That we've been amazed for decades now by the advances in information technology. However, 18 months to 2 years, processor speeds doubled and other measures of our ability to compute improved exponentially. It's starting to slow down. We knew it was going to slow down because there is a fundamental limit imposed by the size of atoms on how small we can make information processors. Meanwhile, experimental physicists were learning how to manipulate, to control, to measure single quantum systems. For decades, most experiments with quantum systems were done on ensembles, where you could read out the average behavior by measuring a system of many fundamental quantum systems. But now we have the ability to address and measure a single atom, an ion trap, a single electron spin, and quantum dot. And we ask, what can we do with those capabilities? Meanwhile, we came to recognize and appreciate that there is computational power inherent in quantum mechanics, which seems to go beyond what we can realize with classical digital computers. And that caused a lot of consternation and interest because of its potential relevance to the security of public key cryptography, which we all make use of in the digital commerce that we engage in every day. So you guys are actually too young to remember, but in 1994, when Peter Shor discovered the quantum factoring algorithm and the efficient algorithm for computing discrete logarithms on a quantum computer, it was really quite earth-shaking. Even I, no computer scientist, realized that something had changed, that this was a phenomenal milestone in science. And what Shor showed us is that problem